So we had a carbocation stability trend. We originally started out with tertiary, better than secondary, better than primary, better than methyl. And we expanded on this a little bit when we learned about vinylic carbocations. It expanded a little bit when we had vinylic carbocations. And you'll recall a vinylic carbocation like this secondary vinylic carbocation is very, very unstable. It's sp hybridized at the carbocation. And we had things like primary vinylic. These were very, very unstable. Again, we had a long lecture about this, about how sp orbitals are more electronegative than sp2 orbitals. If you put a plus charge on it, it's very, very unfavorable. Right? With allylic carbocations, so vinylic were very unstable, but this is a secondary allylic carbocation. It has resonance, stabilization. It has a resonance structure. And this is going to be about the same stability or a little bit better than a tertiary carbocation. Regular old tertiary carbocation that we used to think is the best can actually be bested by resonance stabilization and distribution of plus charge over multiple atoms and sharing of it. Right? This particular resonance structure has another form where plus charge is somewhere else. Rosa, do you have a question? Rosa, I can't hear you. Oh, you just accidentally unmuted yourself. That's okay. If anyone has a question, just put it in there. But the secondary allylic carbocation shares its plus charge here and here. Right? We could actually draw that other form. And so this is a very, very special type of stabilization. It's even better than a tertiary carbocation. Let's just draw on a tertiary carbocation. We'll recall that it has 3 carbons attached to it, and these have the slight ability to donate a little bit of electron density into it. That's better than if we had a hydrogen atom here and it would be secondary. This one pen is just rolling all over the place today. Okay, so these become much more stable due to resonance. Okay, and so whenever we have the possibility of resonance, it stabilizes positive charges very easily. That's the key point about this. So allylic carbocations and resonance stabilization, it's an important point to bring to our attention now. In the second half of this particular course, in 220B or wherever you take the second half of this course, resonance plays a very, very important role with this particular type of molecule, many of which you might know is called benzene, and it has a special characteristic. It's called an aromatic compound, not because it smells, but because if we put plus charge at any position, we have many, many resonance forms. Okay? So this particular compound can have many, many resonance forms. And what you could practice is on your own with drawing resonance structures. Here's a conjugated triene, sp2, 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 sp2. This is a conjugated triene. I'm going to react it with H+, right? I'm going to forget about the counter ion. I'm just simply going to make a secondary carbocation. And what I want you to do with this is come up with 2 unique resonance forms for it where you can move the plus charge. When we have a conjugated diene, the plus charge can end up on 2 different positions, the 1 position, the 4 position. When we have or the plus charge ends up on the 2 position or the 4 position. When we have a conjugated triene, if we put this plus charge on the 4 position by moving electrons, is there any other way we could move more electrons and keep shuffling the charge? Try that on your own, okay? Something I think you all can do. If you really want, there's one other type of carbocation that you could practice working with. This is called a benzylic carbocation. It's related to benzene, but it's not perfectly the same. There's a sp2 hybridized carbon at the end, like a methyl group, where we take off a proton, for example, and we have a plus charge here. See if you can come up with some resonance structures for these. This one's a little bit more advanced than what we did. This is a little bit more than that. But if you figure out resonance structures for these two types of compounds, then you really have mastered resonance to the level you'll need to be successful on our third exam. And if you build up this repertoire right now, this understanding now, it'll be very, very helpful and beneficial to you when you finally do meet aromatic compounds. Okay, so these are just some things you can practice on your own. Probably the text has some problems that I assign that are similar to something like this as well. We're going to talk about an issue that's important with 1,2 and 1,4 addition reactions. We'll figure out why. Let's just put these two words, kinetic versus thermodynamic control. So we're going to talk about kinetic versus thermodynamic control. Kinetics, you'll recall from general chemistry, has something to do about speed. Thermodynamics have something to do about stability. So these two words can be related to speed and stability in our minds to a very rough first approximation. We're going to take butadiene. We're going to look at what happens when it's reacted with HBr at minus 80 degrees Celsius, so very, very low temperature. Right? Very, very low temperature. We make both our 1,2 addition product and our 1,4 addition product. So now I'm just drawing in the things in a more skeletal notation, and I'm only drawing in the hydrogens I've added, the bromine I've added, okay? There's clearly other hydrogens here. There's clearly hydrogens scattered throughout this molecule, but I'm just drawing the ones that I've added in here to show that they've gone on the 1 and 2 positions, and the 1 and 4 position, all right? And that's why we put it like this. And again, just today, I'm going to be consistent, drawing from right to left. If we drew from left to right, we could put it on 1, 2, and 1, 4 position that way as well. Okay, so this would still be called 1, 2, and 1, 4. At very, very low temperatures, this is isolated in about 80% yield, and this is isolated in about 20%. That's the distribution. For you, these numbers don't matter, but you just need to know that this is the major product at low temperature. We could rerun this reaction with HBr at plus 40 degrees. Plus 40 degrees is pretty warm. And we're going to draw the same two products. The 1,2 addition product. And we're going to draw the 1,4 addition product. And the product distribution changes or flip-flops or inverts, and we get 20% of the 1,2 product and 80% of the 1,4 product. So this is a very, very special type of reaction that can be controlled and have drastically different outcomes by temperature. Low temperature, the 1,2 addition product is the major product. High temperature, the 1,4 product is the major product. This first example at low temperature is an example of kinetic control. The reaction is controlled by kinetics. The major product is formed by kinetics. This will always be the case at low temperatures, or for now, when we're learning kinetic control, it'll happen at low temperatures. This other example in the formation of this product at high temperature relative to this is an example of thermodynamic control. So at high temperature, we can kind of keep thermodynamics in mind. At low temperature, we can keep this concept of kinetics in mind. We're going to talk right now about how this happens or why this happens. What's the difference between these two particular products, and why can temperature have such a drastic different outcome on these two things? And to do so, we're going to use our knowledge of reaction coordinate diagrams. You're not going to have to draw any more reaction coordinate diagrams in this class, but I've asked you to draw them with radicals so that we could have intelligent discussions about them throughout this course.